Let's talk about part C, removing the root of a heap. So this happens when you want to extract the node with the highest priority or the smallest key. Okay, how do we remove that? And it's not as simple as just removing the root because you need to ensure that the CBT property is maintained. So the minimum keys at the root, we want to actually remove the minimum key. However, so this is the one to be removed, right? Okay, but we want to ensure that after removing the root, it is still a CBT. So what do? I take the last element here, the last leaf node. Okay, if this were a list, this would be the last element in the list, and swap this with the root. Are we done there? No, because after the swap, which is this situation now in B, we have to ensure that the heap order property is still there. So what do? We check whether this node is in the correct position by comparing it with the two children. In this case, it's actually quite obvious that the left child is actually smaller than the parent and the right child is smaller than the parent. So we need to do a swap. Now, which child to swap with? The smaller child, this one. So before we even do a swap, we have to compare these two children and determine which is the smaller one. Okay, we determine that the left child is smaller. We want to swap the parent with the left child. If that happens, then these three nodes will be in the correct order as far as the heap is concerned. Okay, so we decide to swap. We are here now, state C. We decide to swap the parent with the left child. And this is how it looks like after the swap. Are we done? No. We want to check whether this node is in the correct position by checking 13 with its two children, 15 and 9. By the way, this is called down heaping. Just now, we were doing up heaping. Okay, just now we were inserting a new node, right? Right at the bottom. We want to move it up to ensure that it's at the correct position. Now we are actually doing down heaping. We want to move a node from the root position down until it is at the correct position. So here we check 15 versus 9, which is smaller, 9 is smaller. And we check 9 versus 13, and we perform a swap. Here, perform a swap, and this is the outcome. F is the outcome. We are not done yet. We have to check if this one can go down some more. So which is the smaller child? This one, the right child is smaller. 14 versus 12. 12 wins, huh? And then I'll compare 12 with 13. A swap is required. So we do a swap here, and this is the outcome. So we stop at this place because this is already at the root level. I mean, at the bottommost level, it is already a leaf node, and it cannot go down anymore. Remember, in down heaping, we stop either when we reach the lowest level, it is a leaf node, or we stop when it is in a correct position. That means it is actually smaller than both its children. These are two stop conditions for a down heap operation. So this will be the code. I want to remove the minimum. So to remove the minimum, I just grab the element at position 0. That is the smallest minimum element. Store it in a temporary variable to be returned in the last statement here. Now, meanwhile, I will swap the root, the element at position 0, with the element at position, the last position. So this is the latest leaf, or the leaf at the lowest level. Okay, so as far as an array is concerned, right, I just swap this with the last element. Just do a swap. Okay, it will be this situation. This is at position 0 and this is at position n. Okay, Then I remove the last element in the heap. After swapping, I just throw this away. Okay, that was a previous previous root. And then I perform a down heap. Perform a down heap, I pass in position 0. So this element may not be at the correct position. So the down heap happens here. So while loop here, remember two stop conditions. I stop when the current node has no left child. So as long as it has a left child, I go into the while loop. When it has no left child, that means the current node is a leaf node. I stop there. This is the first stop condition. Now the second stop condition will be here. Okay, when the current node is smaller than both its children. These are two stop conditions. Let's go into the while loop and take a look. Now, the code here to here basically compares the left child, this one, and the right child to determine which is the smaller child. And I will store it in this variable called small child index. Okay, the small child index may be the left child's index or the right child's index. Okay, so initially I set it to the left index, and then I will check this against the right child, which is actually bigger, which is actually smaller. So if the right index, the element at the key at the right index is actually smaller, I will change the small child index to the right index. Okay, so once I've determined which is the small child index, the left or the right child, here I will actually compare the parent with the smaller one, whichever, left or right. So if the heap is, if the small child index is actually bigger than the heap, that's good. That means the parent is at the correct position. I will break, and that's the end of your down heaping operation. On the other hand, okay, if the parent is smaller than the small child, whichever the smaller child is, left or right one, I will perform a swap. This statement does the swap. I swap the parent with that small child. Okay, and then J is the small child, and I repeat the while loop. Okay, I hope this is easy to understand. Now, let me talk about this time complexity, the complexity of an insert, let me say NQ, and a DQ or remove min. Now, when you perform an insert, remember when we were talking about how to perform insert? Let's say this is the current heap. To perform insert, right? This is the position of the new node. There is a chance that I'll have to bubble up when I perform an up heap operation. In the worst case, how many swaps do I have to make? 1, 2. Okay, no matter the current size of the heap, when I actually perform an insert, in the worst case, the maximum number of swaps I have to make to ensure that, it is still a heap is actually H. I have to make H swaps. And H is bounded by log n. We have determined that earlier. And that is why the time complexity, worst case time complexity of the insert operation is O log n. What about remover? Remove min. Okay, let's say this is the existing heap of height 2. In order to remove min or the root, what do? I have to bring this up, replace the root with this. So this one, the shaded one, goes to the root now. After the root is returned to the caller, I'm left with this binary tree, this complete binary tree, which may not be a heap yet. And I have to bubble down. I will do a down heap. And again, the worst case, how many swaps do I have to make? H swaps, where H is the height. After H swaps, your new root is going to be at the leaf level, at the lowest level. So again, H is bounded by log n. So in the worst case, the remove min operation is going to be O log n. Can? I'm going to spend some time talking about adaptable priority queue. Now, in most circumstances, a priority queue is going to be, so this is a priority queue, right? It's going to be an abstract data type. It's a black box. The user or the client of the priority queue is usually not very concerned with what happens in the queue, as long as this queue has a good time complexity, as long as this priority queue has a good time complexity. However, in some situations, you may want to modify the elements already in a priority queue. For example, I want to replace the key of an element already in the priority queue. It's not a usual operation. Like what I've said, a client using a priority queue usually does not reach into the priority queue and modify the elements already in the queue. But well, sometimes you want to do that. Let me give an example. To prevent starvation. Let's say you have an element in the priority queue with a low priority. And then along the way, new elements with higher priority always gets inserted or enqueued. Okay, and this may result in that low priority element being stuck in a priority queue for a very, very long time or even forever. So it is possible to come up with an algorithm to actually increase the priority, in other words, reduce the queue, the key of elements already in the priority queue for a long time. Okay, after a certain period of time, I don't know, X seconds or what, or one day, you may want to change the key by calling the replace key operation so that the priority is higher. So this is an example of a reason why you may want to modify elements already in a priority queue. So let's take a look at the replace key complexity. It is log n y. So this is the heap. Let's say this is the key I want to replace. I want to replace the key of this particular node. So once I replace the key, it may not be in the correct position anymore. Okay, I will have to check whether it is smaller than both its children. If not, it will swap. I will have to check whether it's actually bigger than the parent. If so, that's good. Okay. If it's smaller than the parent, I have to do a swap. So I may need to down heap. I may need to up heap if the key of this node is changed. Again, the worst case, how many swaps do I have to perform when I do a down heap or an up heap? H swaps. So that's why in the worst case, a replace key operation is going to cost O log n. Can? I'll move on to the next slide. This is an in-class exercise. So I'll do part of it and I hope you can finish the rest. I'll give you the final solution. Now, so the situation here is that the heap is originally empty. It's an empty heap. Okay, operation 1, I insert 4. So automatically you'll be the root. I mean, if this were an array or a list, right, you'll be at position 0. So I'm a bit lazy. I don't want to write the corresponding value there. Anyway, we are just focusing on the key. Insert 37. 37 will come here. Okay. So ensure that it is still a complete binary tree. And then step 2, I have to check whether I need to up heap this or not, whether I need to bubble up. So 37 is bigger than 4, end of story. Okay. Third operation, insert 91. 91 will appear here to ensure that it's a CBT. I need to check, is 91 in the correct position? Is there a need to bubble up? No, because 91 is bigger than 4. Good. Step 4, insert 22. 22 will come here. Okay, is it in the correct position? No, because 22 is smaller than 37. So I do a swap in my up heap operation. I swap these two. 22 comes here, 37 comes here, 4 and 91. So I need to check whether 22 is bigger than 4. Yes, end of story. Okay, so this is the current state now. Remove min. Now, when I remove min, 4 goes out. The element, the root goes out and gets returned. So 37 will be swap with the root. So this will be the outcome of the swap. And I will perform a down heap for 37. So I get the smaller child. This is a smaller child. And I compare the small child with 37. Oh, there's a need for a swap. So I'll swap 22 with 37. 22 becomes the new root. 37 is the left child, 31. And that's the outcome after step 5. All right. Step 6 will be, insert this new node. And this is, I need to check whether 82 is bigger or smaller than 37. It is bigger, so it is in the correct position. So please carry on trying this. Pause for a while. I'll give you the answer after all 13 operations. Okay, I hope you guys have attempted this. The final answer after step 13 looks like that. This is the final heap. All right, that's it. If you don't get this answer, please ask. Make an appointment with one of your faculty members or TA and ask. Okay, the last slide before we pause for the next unit. Time complexity. What is the worst case time complexity? To insert n keys into an empty heap. Okay, like what we were doing here. These are insertions. The initial state is that the heap is empty. If the keys are inserted one by one. You want to pause for a while to think about this? Okay, let's take a look at a CBT here. Okay, in this case, let's take a look at a full binary tree. You might realize something interesting. The number of nodes here and number of nodes here. Total number of nodes is n, right? Roughly half n nodes will make up the upper part of the tree. Okay, level 0, 1, 2. Now, about half n nodes, or maybe lesser, depending on how many gaps there are on the lowest level. Half n nodes will come from the lowest level. Or maybe a bit less than half n. In the worst case, let's assume that the last level is filled and no gaps at all. So in the worst case, I need to actually insert all the nodes into the CBT so that there are no more gaps, even at the last level. So to insert an element here, you may have to perform how many swaps? H swaps, because you are doing this upheap thing, right? So in the worst case, to insert an element on the last level, you have to perform H swaps or locked n swaps. So locked n swaps in the worst case for n over 2 nodes. What about those at the top here? Now again, there are n over 2 nodes, but in the worst case, to insert them one by one, how many swaps are required? Is going to be lesser than log n. Lesser than log n. Do you agree? For example, to insert this one, at most 1 swap. To insert this one, at most 2 swaps, which is smaller than the height. Definitely smaller than the height. So the total number of swaps will be this plus this. Okay, which is O log n. Sorry, O n log n. Forgot this thing. N times, n over 2 times log n. Number of swaps. So the worst case time complexity to insert n keys one by one into an empty heap is O n log n. It's upper bound, worst case. In the next section, the last section, we are going to show that, if we already have the n keys, we already know what are the n keys, right? To be inserted into a heap right at the beginning. we can actually perform this insertion in an O(n) operation, in an O(n) way, which is better than O(n) log n.